My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 483. In this lecture, we will try to understand divisive hierarchical clustering and dendograms. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 482, in which we discussed about agglomerative hierarchical clustering. Agglomerative hierarchical clustering starts with individual points. Just try to recall. It starts with individual points and groups together. What is the idea? And groups together, isn't it? Groups together, whereas divisive does exact opposite. Which one? Divisive. In this lecture, we will try to understand divisive hierarchical clustering. This does exactly opposite. Let's also see how does divisive hierarchical clustering works. Divisive exactly works opposite to opposite. Divisive starts off saying everything is one big cluster, isn't it? It's just like a big cluster. So divisive starts with one big cluster that contains all the points in the first iteration, isn't it? That is the idea. In the second iteration, divisive would say, can I break up this big cluster into two small clusters? So divisive will start grouping points. It tries to break divisive, as word says, it tries to divide the large cluster into small clusters. It tries to divide the large cluster into smaller clusters. In third stage, in the third iteration, it will probably break up this into clusters like, just see, this is, it tries to divide the large clusters into smaller clusters, isn't it? Just in initially, in first iteration, it has one cluster. In second iteration, it has two clusters, isn't it? In similar manner, what happens in third stage? How many clusters do we have here? This is one cluster. This is second cluster, third cluster, fourth cluster. This is iteration number 3. In iteration 3, we have 3 clusters, isn't it? Yes. In third stage, in the third iteration, it will probably break up this into clusters like this, isn't it? How many clusters we have? We have 4 clusters, isn't it? It will keep breaking up. It will keep going on till the time we have how many clusters? Till the time we have 13 clusters. If you consider here, how many points do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Therefore, it will keep going on till the time we have 13 clusters. Each cluster effectively becoming a single point. So, divisive starts with one big cluster with all points, one cluster with all points, and it reaches how many clusters? It reaches 13 clusters, isn't it? One cluster for each point. Agglomerative does the other way around. Agglomerative is the more popular one, that is typically studied, that is typically implemented and used. There is one problem with divisive clustering is there is one problem with the divisive clustering is how to divide is the big question. This is seldom used. People typically use agglomerative because trying to group things based on similarity or distance is easier than trying to break things. I'm not saying this is hard or impossible, but agglomerative is more popular. Now you understand why it is called hierarchical clustering. Because if you think about it, there is an hierarchy. Because if you think about, there is an hierarchy, but remember the key ingredient for agglomerative clustering, trying to group things based on similarity or distance. That's a first. That is one important point. The key ingredient for agglomerative clustering would be similarity measure or distance measure between not just points, between clusters. So if you give me two clusters, I should be able to quantitatively measure similarity or distance, because we are grouping similar clusters or nearby clusters. So we need to have sense of how to measure similarity or distance between the clusters. Once if we have this algorithm is very good. It is straightforward, isn't it? There is other way to visualize or to understand hierarchical clustering. Again, we are back to the same slideshow. Just see here, the same slideshow that we used for k-means clustering. This is very nice slideshow which has lots of beautiful diagrams. I will provide link to this reference. I will refer to this PDF in the descriptive section of this video. Coming back to this, let's imagine I have these 6 points. What are these? 1, 2, 3. I have these 6 points. Just try to understand. 1, 2, 3, 4, 5, 6, isn't it? I have the 1, 2, 3, 4, 5, 6. So just ignore these red ones. Just let me ignore these red ones. Just what I am doing, just ignore these red ones initially. Let's just ignore them for simplicity. So you have 6 points. What are those 6 points? Those 6 points are 1, 3, 2, 5, 4 and 6. 1, 2, 3, 4, 5 and 6. 1, 3, 2, 5, 4, 6. Isn't it? That's what it says. Yes. Yes. If you notice here, you have point 1 and point 3. Just see, this is point 1, point 3. Point 1 and point 3. 2, 5. 2, 5. This is 2, 5. And this is 4. This one is 6. Isn't it? On x-axis, I'm taking all these points. Which points? Point 1 and point 1, point 3, point 2, 5, 4, 6. I'm taking all these points. on x-axis. In agglomerative clustering, since 1 and 3 are closed, just see here 1 and 3 are closed. Since 1 and 3 are closed, first grouped into one cluster. Just see, point 1, point 3 are closed. They are grouped into one cluster. Let me say this is C1. Isn't it? That's what it says. This is C1. This is C1. As these 2 points are closer, I am combining them into cluster C1. Similarly, 2 and 5 are also closed. Just observe this one. 2 and 5 are also closed. This is C2. Just see, this is 2, this is 5. Therefore, this is C2. Just I am combining as another cluster. Similarly, 2 and 5 are also closed, and hence 2 and 5 are also grouped together into one cluster. Just see, 2 and 5 are grouped together into one cluster. So if you notice, you are trying to build a tree-like structure. We understood what tree is look like, because you have seen lots of like trees, decision trees, KD trees, extra, isn't it? In this type of tree, what we do here is we are taking these point 1 and 3, and since they are close, we are grouping them to create a cluster. Let's call them cluster C1. Similarly, 2 and 5 are close enough. We are grouping them and creating cluster 2. My point 4 remains cluster onto itself, isn't it? My point 4 remains cluster onto itself. 6 also remains cluster onto itself. Just see, point 4 is a cluster. Just see, point 4 is a cluster C3. Point 6 is also cluster C4, isn't it? That's what it says. Yes, you can understand this. Yes, I am grouping 1 and 3. Yes, I am grouping 2 and 5. So in the next iteration, at the end of first iteration, I have 4 clusters. Cluster 1 contains 1 and 3. Cluster 2 contains 2 and 5. I have cluster 3 contains only 0.4 and cluster 4 contains only 0.6. Now in the next iteration, I see that my cluster 2, which is this cluster, isn't it? In next iteration, what happens? Just see, in next iteration C5 means what? Now in next iteration, I see that my cluster 2, which is this cluster, isn't it? This cluster 2, 5, isn't it? My cluster 2, which contains which contains this 0.2 and 0.5, isn't it? 0.2, 0.5. This is cluster 2, which is this cluster, and my cluster 3. What is my cluster 3? My cluster 3, C3 is 4, isn't it? My cluster 3, which contains 4. They are close to each other. I will group both of them. Just see, I am grouping C2 and I also grouping C3, and I am naming as C5, isn't it? Now in cluster 5, what I have, which is combination, my cluster 5, which is the combination of cluster 2 C2 and cluster 3 C3. I have cluster 4 and cluster 1 also. My cluster 5 is close to cluster 1. This my cluster 5 is close to cluster 1, isn't it? That's why what I am doing. My cluster 5 is close to cluster 1. So I will group both of them into one large cluster here. By grouping both of them, I am creating another cluster, that is cluster 6, isn't it? Just you can understand, that is cluster 6. This is a big cluster. Finally, I am combining 0.6, which is cluster C4. If you think of it, we construct a tree or hierarchy. When you have a tree, there is an hierarchy. Actually, what is this tree? This tree actually records. What happens? This tree actually records sequence of mergers or splits, isn't it? What is the order that you merge these points? This is hierarchical structure, as it is tree-like structure which records the sequence of merges. This tree in data mining or in clustering is often referred to as dendogram. This tree is often referred to as dendogram. A dendogram is nothing but a tree which records the sequence of merges in case of agglomerative clustering or splits in the case of divisible hierarchical clustering. So we typically use agglomerative clustering. We mostly talk about merges rather than splits. So one thing you notice from this structure is when we do agglomerative or divisive clustering, we never mention the maximum number of clusters. Once you build the hierarchy, if you want 5 clusters, if you want 5 clusters, you will get 5 clusters, isn't it? If you want 5 clusters, just you can stop here. If you want 5 clusters, just you can stop here. If you want 2 clusters, you can stop here, isn't it? If you want 2 cluster, we can stop in stage 4. 2 clusters means this is stage 1, stage 2, this is stage 3, this is stage 4. If you want 2 clusters, just stop at stage 4, isn't it? If you want 9 clusters, you can stop at step 2, stage 2. This is stage 1 or step 1, that is step 2. If you want 9 clusters, just you can stop at step 2 or stage 2. You can stop wherever you want. You don't need number of clusters as hyperparameter. You record number of clusters in k-means is a hyperparameter. For agglomerative clustering, there is no need to give number of clusters as a hyperparameter, because once if you clustered, you can say, let's assume you clustered using agglomerative clustering. First, let's say you wanted to see 2 clusters. You can look at the 2 clusters and you can say these clusters are not good. You can say these clusters are not good. Let's go into more detailed structure. You can get 5 clusters, isn't it? If you want, you can get 2 clusters. If you want, you can get 5 clusters. You can get 5 clusters. If you want to go finer structure, then you will go to, if you need finer structures, then you will get 9 clusters. This is not possible with k-means. That's important. This is not possible with k-means. In k-means, if you are trained, trained your algorithm, if you train your algorithm with k equal 3 in k-means, if you got 3 clusters, C1, C2, C3. If you got 3 clusters, C1, C2, C3. Now, if you want 5 clusters or 7 clusters, you just have to retrain. If you need 5 clusters, you have to retrain, isn't it? If you need 7 clusters, again you have to retrain. Redo k-means with k equal to 7 to get 7 clusters. There is no way to go from 3 clusters to 7 clusters easily, but in the case of agglomerative clustering or in divisive clustering, in the case of hierarchical clustering, you can go from 2 clusters to 5 clusters. You can go deeper and deeper into the structure of the data very, very easily without having to recompute. This is one of the very, very useful, very useful reason, important property why agglomerative is very, very popular and it is good alternative to k-means. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.